So go through more examples about AI logic and stick diagrams. And there will be a quiz on two non-logic. Very doable. Let's make sure everything is covered before we do the quiz. Okay. So for example, the NAND gate from last time. It's a NAND gate, right? Two gates, two in parallel, one wire introduced from the power source and merged as these two nodes. And these two NMOSes are in series. Okay? And then just label, here's A is NMOS on the top, so this must be A. Label it A, B, B. But in your electric VLSI, you have to short them using a poly, which is fine because this is just metal one, so they're not shorted, right? So that's a NAND gate. And if we look at the truth table, maybe the out 0001 1011. Right, it is one all the time, one all the time, except these two inputs are both ones. So in that case, you can see for these outputs, it's using the PMOS to put it up to VDD. Okay, so these outputs are managed by the PMOSes, and this is managed by the NMOS. Because only PMOS is pulling things up, right, and NMOSes are pulling output down to ground. If you look at these inputs, 000110, so if you just look at the inputs, you just have to have one of the inputs, at least one of them to be 0 in order to short it to power supply, which makes sense. That's why you put two PMOSes on top in parallel, because either one is on or both of them are on, it's shorting this one to VDD. Okay, so this circuit comes from this logic. For the NMOSes, both have to be 1 in order to turn it on, so they have to be in series. So both have to be on. That's just one channel. Okay, and it's giving a 0 to the circuit to the result. Is there any question on this one? I didn't burn a quiz. I'll burn it on Friday. But any question on this? This is a solution to the quiz on Monday. All right, easy. Another note here, if you have two parallel transistors, this will be a part of the lab on Thursday this week. For example, each one is W over L, and apparently they are in parallel, right? So for the layout, for two transistors in parallel, the layout looks like this. These are the vias. And there's a channel in the middle. The drawing is weird, but you know what's going on here. So these are the two transistors. So for two parallel transistors, how do you connect them? You can definitely merge these two nodes, right? No problem. What about the channel? You can see these. Like one transistor, another transistor, and you merge the middle node. So I'm having two separate transistors, which is fine, it's equivalent. Okay, so you need, if you are not merging the middle node, you need to connect the two middle nodes with the metal one. This is metal one. Okay, it's just method 2. Okay, this is method 1, you merge the middle node, or you don't merge the middle node but use the metal one to short them together. It's still the same thing. And this is equivalent to what? to just one transistor. So basically I should draw the gate thicker because the gate defines the channel's length. So this is equivalent to one big transistor with 2W over L electrically. Everyone is W over L. If I merge them into one big transistor, wait, am I changing? What did I do wrong here? So if I short it this way, what's really happening? Am I doubling the width or length? So where's the current? What's the direction of the current flow? Through the channel, right? If I do it this way, am I doubling the width or length? If I merge these two, for example, here is one unit, another unit, and merge them into the two transistors into one bigger transistor, am I doubling the width or length of the single one? The length, because that's the channel, that's the current flow direction, that's the length. Okay, so this dimension here is the length. So this becomes what? 2L. Did I change the width? No, because this is the width. Eventually, if I merge these two like this, it's basically giving me what? W over 2L. Because the current flows that way. So that's the length of the trip of the electrons, right, or holes. That's the width, keep in mind. So this is not for this circuit. I did it wrong. So this is for what? For this circuit schematic. W over L. This is equivalent to W over 2L if they're in series. If they're in series, then this is equivalent to W over 2L. So what about this? How should I connect this one in layout as a parallel circuit? So this is one, okay? So for parallel one, it's different. The Vs. Metal 1. Are they in parallel right now? Are they in parallel? What is the length? Here's the length. Am I changing the length? Nope. Am I changing the width? Yes, I'm doubling the width. Because here is the width of the channel. So this becomes 2W over L, right? I can use a one bigger transistor to reach the same electrical property, okay? In terms of driving capability, the parasitic capacitance inside and everything, a lot of those things are equivalent. However, because there's just one gate, if you do a LVS, it won't pass because there are different circuits. This one has two gates and this one has one gate. So it won't pass LVS, however, electrically they have the same property, the driving capability and all those kind of things. They're equivalent in terms of driving capability, but not passing LVS or NCC. So NCC in electric vehicle SI, so it's not going to pass it. So now let's come back to the AOI example we introduced on Monday. Look at the example. Or BC. If we don't use the AOI logic, what's going to happen? Let's compare. A, B, C, right? Inverter, and logic, or logic, done. That's for the circuit. If we convert it to layouts, it looks like this. Power rails. Got an inverter first. That's an inverter. Okay, that's A, right? A is shorted to each other, so that's A. Signal input, and that's a drain for the PMOS and NMOS. That's the signal output. And you need an AND gate. So AND gate, you need a NAND gate first and then invert it. So NAND gate has two PMOS on the top in parallel, and two NMOSes at the bottom in series. That's a NAND gate. And that needs to be inverted. So output goes to the input, and eventually that's the AND logic. Right? So these ones are the gates. B and C, right? So it's going to be B and C. I know they're shorted, but just in case, you know, this is different layer. Okay, so B and C are inputs for the gates, and that's the output. That's a NAND gate logic, and goes to the inverter's input, and that's the inverter's output. So that's forming an AND gate because the NAND gate inverted, so it's not getting AND gate. For OR gate, you need two PMOS on the top in series because NOR gate looks like this. That's a NOR gate. A or B AND, inverted, so A or B NOT. That's the NOR gate. So NOR gate have two PMOSes on the top in series, and two NMOSes at the bottom in parallel. Okay? That's a gate. It's taking output from the inverter, which is here. I know you are not going to do it that way, but just showing you the connection. Okay, there's nothing can go beyond the power rail. Everything has to be within that power rail. I don't have a different color here. So inverter's output goes to the input of the OR gate, and AND gate's output goes to the input of the another input of the OR gate. And here's the final output, which is A NOT or BC. Right? So that's the traditional way of doing this. You can tell it's very complicated. Takes time and space, have a lot of empty areas, a lot of transistors. So it's bad, it's pretty bad. You guys are like, why did you teach us a bad thing, bad example? Just showing you a traditional way to do that, okay? So now if you look at the AOI logic, it's going to be totally different. And that is why we are doing it through that AOI logic. So looking at this one, and this one can be converted to this, okay? Being inverted twice is still the same thing. And because we know that every time we draw AOI logic, there will be a bar on the top. The reason for that is when the input is 0, is opening up the PMOS and shorting this one to the VDD. In that case, 0 will give it 1. That's why it's always getting inverted, right? So that's why it's called AOI. It's AND, OR, and invert. It's AOI, okay? AOI. And that is why we want to keep a bar with it. It's the one bar on the top, okay, for all the logic, just one universal bar on the top. And since we know that De Morgan's law is basically splitting the bar and change the sign, so we can split this bar and change the sign. So basically it becomes A naught naught and B C naught and bar, right? Split this bar and change the sign. So A naught naught, change the sign, B C naught. And this is A and B C naught. And this is also A and B naught or C naught. Okay? So now we are ready to draw the AOI schematic, because according to the experience we have, or the conclusion we have, we know that think about the NAND gate and NOR gates, right? So for the NAND gate, if you have AND logic under the bar, so you are having a parallel PMOS and NMOS is in series. If you have an OR logic under the bar, and you need the PMOS in series and NMOS in parallel. So that's a conclusion, okay? So in that case, by looking at this one, we know that if we treat this one as a big box, so the A signals transistor of the PMOS should be in parallel or series with this box. It's a non-logic. It's an AND, not. It's a non-logic. So A signal and this whole thing need to be in parallel for PMOS. Okay, whatever in here. So you know that there will be something in parallel here, okay? And because it's OR logic, always think about the NAND gate. OR logic, you have PMOS in series. So these two signals have to be in series. So that is B, or just directly use B naught and C naught. B naught and C naught. And at the bottom, because this is in series, you'll know that you have to, so signal A and this block are in series. And B naught and C naught, the NMOSes, are in parallel. Okay? So compare to this schematic, you can tell we're probably using less number of transistors. Maybe. If you count the inverters, probably not. But just looking at the circuit, this is way easier. And you can definitely simplify your layout as well, because you know how to do it using stick diagrams. Okay, so you don't have to draw every single transistor separately, like this. It's taking a lot of empty space. So in that case, let's just convert this guy to its stick diagram and see how much we can simplify the layout to save space, because space is so expensive on the chip. So how to convert this one to the stick diagram? 3 transistors on top, 4, 1, 2, 3, 4. So we need a 1, 2, 3, 4, 5 nodes. Power rail. And 90% of the chances you can have everything in one line. Okay, just do a one-liner and eventually can figure out the parallel and series transistors. And now let's see if this is the case this time. How do we deal with top transistors, these ones? wait. Okay, yeah, that's right. Okay, so it's actually this 3. Sorry, 3, not 4. It's easier. 1, 2, 3, 4. Let's deal with the PMOSes first. So go through A first, right? Go through A first, and then these two are in series. This is really simple, right? Just this, right? So that is A. That is B naught, C naught for the gates. So the current flows from the VDD and goes through this transistor first, and then goes through these two series transistors. Right, eventually merge here. Any question on this? A lot of questions. Are we getting that? What's that? See, you can actually treat these two in series as one transistor. Remember when we do the NAND gate, right? When we do the NAND gate, 1, 2, 3, so 2 PMOSes. How do we do it? One current flowing down, so it's a metal 1 wire here, and then it's getting split into 2 branches and merged over here as metal 1, right? So that's definitely 2 transistors in parallel, no problem. No problem on this, right? Any question on this one? 2 PMOSes in parallel. This makes sense, right? Current split in 2 branches, equivalent branches, and goes through these 2 gates and merge. 2 PMOSes in parallel. For this one, not really not that different. So 1, 2, 3, 4. So what about you just treat these 2 serial transistors as one transistor? So there's like 1 current flowing down from the VDD and going through this one, going through 2 instead of 1, right? And then merge. Okay. What about the bottom ones? Let's keep using this guy. That's the same thing. So let's draw the bottom rail. 1, 2, 3, 4. 1, 2, 3. And look at this circuit here. How do we convert it to a stick diagram? There's a signal line comes down from the PMOSes. It's over here, right? So first, it has to go through A first, and then you got 2 parallel transistors. So you can do this. No. Do this. A, parallel, go to the ground. A, right? So go through A first and then split. So go through A first, split. How do you split it? One goes through here, one goes through here, and merge. Questions? Let's figure out the signal lines. Which one has to be A? This one has to be A. Okay? These ones, they are not equivalent because the signal goes through A first. So whenever the signal comes down from the top, the first transistor has to be A. So this gate has to be A. And now let's see. Is this A as well? VDD. We got 1 PMOS and two PMOS in series. 1 and 2. Is this A? Yeah, luckily it's still A. Why it's good? Because all these are metal ones. I can directly draw a straight line to connect the poly together. They are the same signals, which is signal A. What about B and C? Or B naught and C naught. So these are signals already inverted, B naught and C naught. Does it matter which one's B naught and C naught here? Does it matter? Yes, because VDD signal goes through B naught first, and then C naught. So which one has to be B naught? This one. This has to be C naught instead, because the current flows that way. So first leg has to go through B naught first. So what about these two transistors? Are they equivalent? Yes, because they are in parallel, so they are equivalent. Whenever the current comes down, got split in two branches, they are equivalent. Doesn't matter which is which, depending on which one is B naught on the top, because this one cannot be changed. So we all know which one to be B naught. This one to be B naught. Why? Because in layout, you can directly draw a straight line to connect the poly together. So this has to be C naught. It's one straight line. Can figure things out. Now, let's come back. Okay, I didn't change anything. If you compare the two circuits, which one do you prefer? This or this? Okay, apparently you want to do this. Okay? Saving a lot of space. It'll be faster and smaller. Let's see more examples. Don't worry about that. More examples.
So are you taking B naught and C naught as inputs for the electrical system?
Yeah,
So it's just not part of the transistor line?
that is right. So I didn't draw the two inverters,
Okay.
but I can draw the inverters really easily, right? It's still because this whole thing can be really compact. It's probably the whole thing here is maybe similar area like this area, you know. You just have to add another two inverters, right? So the signals has to be inverted somewhere else.
Okay. But
Yeah.
then the one above, the one you were originally looking at, that one doesn't need any extra inverters.
Yeah, this one doesn't need any extra inverters, I believe. Yeah, because the signal lines are directly A and B and C's, right? Yeah. But I can imagine if you have, that's not a good example. I think the main thing is if you have separate gates, there are a lot of space in the middle to have all the vias, and because poly are gates and inputs are polys, you have to drill a hole to the metal one layer using a via, right? So in that case, it has a lot of space because the design rules they are requiring that kind of spacing. So results in a lot of empty space in the middle. Okay, that's the main downside of it. So there will be an example for the slider, and you can compare the total layout area really easily. No internet connection. I think this is a good example for that. Same slider circuit. You can see if you use the AI logic to simplify it, looks like this. Okay, the traditional slider looks like this. It's the same functionality, same logic. And eventually, I think we have a simulation shows that this is a lot faster. Just looking at the rising edge of the circuits, and this charges way faster than this one, which makes sense because you can see this has a lot of parasitic capacitors. Every transistor has the gates and it's charging and discharging all these parasitics, but this one definitely has less, right? But eventually you can tell it's saving a lot of space and also increasing the speed of the circuits. Right. Okay, can we start the next example here? What's the first step? Two bars. Split the bar and change the sign. I just factored out C for these two terms. So it's going to be B naught or D and C and bar, because that bar getting split. Split the bar, change the sign. What's the better next step? A naught and B naught and or D naught or C naught bar, right? I split this bar and change that sign to or, and I split the bar as well, right? So next is A, B naught naught and D naught. Okay. Yeah, I think this is what I want. So these two bars can be cancelled. Right? Now we convert it to the schematic. Okay? See what that looks like. Where should we start with? A, right? A naught. A naught. It's a NAND gate, right? It's a NAND gate for this logic. This is a whole block here. So these should be in parallel. Okay? These should be in parallel with this whole thing. It's A naught PMOS. And you have D, because this is a NOR gate, so this and this should be in series, and this should be in parallel. We're having BD and C naught. B, D naught, sorry, D naught, and this is C naught. And because it's a NAND gate, so for A naught has to be in series with the whole thing. Okay, and these are in series, is in parallel. This is OR logic, so it's in OR logic are in parallel, right? And these are in series, so you are having B D naught in parallel with C naught. Okay? Just keep in mind, it's really actually really simple. You probably want to write a note somewhere when you are working on this kind of problems. Okay? So if you see an AND logic are having a series PMOSes, have an OR logic, AND logic, parallel PMOSes, OR logic, series PMOSes. Layout 1, 2, 3, 4, and then 5 nodes. 1, 2, 3, 4. Can I make it in one line? Let's try it, right? So you need 1, just going that way. And for the rest, you need a parallel, 2 in parallel first and then 1 in series. This can be tricky. Plan for the rest of the transistors so you can make that happen. So 2 in parallel and 1 in series. How could you make that happen? It's hard. However, logic-wise, could you convert? Why is hard? Let's see. So, for example, I want to make these 2 in parallel first, because this current goes down and goes through A0, so this is done. Comes to the end, it's done. So I need to deal with the other branch on the right. Okay. So how do I deal with it? I need a 2 parallel first. So because this is a major node, how could I make 2 parallel transistors at the same time? Yes, I probably can. What I can do is I can have this one goes to here as well, so it's merged. So it's getting merged over here. I'm getting 1 node merged. So these 2 are in parallel, no problem. But the problem is how to connect the C0, this PMOS transistor, to the output. The output becomes in the middle. See? The output of these 2 parallel transistors are in the middle. There's no way that I can connect to the source of the other PMOS, because the other of the PMOS is over here. How do you make the connection? Nowhere to go. You're seeing here. You are shorting the 2 nodes of this transistor, so it doesn't work. Here. What's going to happen? So if you short it here, which means you are trying to flow the current that way, and you are treating this node as what? As this node. But it's not. It's not. This node is what? VDD. So you are basically shorting this one to VDD. It doesn't work. How do we deal with it? Because these 2 are in series, and electrically, it doesn't matter if I swap it. This is still an equivalent circuit. I change this single transistor to the top and 2 parallel to the bottom. It's not changing anything. But you have to change your layout accordingly, so it's able to pass NCC or LVS. It's D0, okay, it's D0. Why this will work? Let's take a look. 1, 2, 3, 4, 5. Still introduce 1 wire here from the top, so it's going through this one as A0. It's A0. Because I have C0 first, so it's easy to deal with that single transistor, so it's going to flow to this point, no problem. So this becomes C0, right? And then I'm going to do a parallel transistor here. So whenever this one flows through C0, reaches this node, and this is 1 node, so it's split in 2 branches and merge at this point. So this point becomes this point. So they're equivalent. So you can pass LVS. How much did you get from this kind of technique? 20%? No, not even 20%? 30%? 10%? 0? Really?
So, could you point to where the gates are on the stick diagram?
The gates are the little stick in the middle.
Correspond to the actual diagram. It's like the gate is the line. Yeah.
This line is a gate. That's a diffusion. That's a channel.
Yeah, the drain and the source,
drain and source, yes.
So then wouldn't the VDD have to go on the other side of the A gate because VDD isn't going to C at all?
I'm not getting that. Can I say it again?
So VDD goes to A
Yeah,
and B and D,
yeah,
but it doesn't go to C.
nope.
But there you have the C gate as just to the right of the A gate.
But I have C here swapped to the top. Right? So now VDD goes to A first, and then goes through C as a second. And now it's split into two branches. Split.
I'm a little confused about the wires, like at the beginning, sort of like solving that.
Wires here or here?
Just like up a little bit, like where you have
Here?
two lines, like when you start the equation,
Uh-huh.
or the top of the equation.
Yeah? Oh, yeah, there are two NOT gates, inverted twice. So if you have logic inverted twice, it's not changing the logic, right? 8 not, okay? It's not changing the logic. So eventually I'm just keeping the top bar, which is the top bar here, but the bar in the middle getting split according to De Morgan's law, because if you split the bar and change the sign, it's not changing the logic.
I see that.
Yeah.
One of them will represent the wire.
No, these are the logic operator. It's not a gate, inverter. None of them are wires. It's logic, right? Logic operator, not. Okay. And eventually, you look at this circuit according to the NAND gates and NOR gates here. Okay, because NAND gates, and we find out NAND gates is AB not. NOR gates, we find out NOR gates, if we draw a circuit like this, it's going to be A or B not. So that's a conclusion, okay? We can use this model to find out all the other more complicated circuits like this. So because we know this kind of structure, every time when the PMOS are getting a zero signal, or because all the signals are being shorted to both PMOS and NMOS. So the thing is, whenever we have a zero input, it's always turning on the PMOS. So zero input, you are getting a 1 because it's turning on the PMOS, is putting this up to 1. Okay, so that's why it's always getting inverted, and that's why the logic eventually giving you this kind of structure, because you have a bar on the top always. If you directly draw a circuit using the PMOSes and NMOSes, it's always getting inverted because of that. And we don't have to dig too deep into that theory because it happens. It's already what's happening. Okay, so in that case, when we can design it backwards. If we see a logic like this, we want to form it. We want to form a logic expression which has a bar on the top. So we can directly draw the circuit like this. Eventually, it will be serving that logic expression. Since we have the conclusion over here already, we know that if we draw a circuit like this, it's going to be inverted eventually. Okay, so that is why we are trying to get a bar on the top first. That's just a method. Okay, what's that?
So, when you have that logic equation, when you are trying to do the schematic from it,
Yes.
are you putting 2 transistors per the letter, for it's logic 0 and logic 1? Is there 2 transistor for each letter? Is that corresponding?
Yes, because you can see B, right?
Yes.
Yeah, they are electrically shorted. I just didn't draw the lines. There are too many lines to draw. Will be tangled.
So, for example, in that last one,
Mm-hmm.
we have 2 C's, then we are gonna have 4, yeah.
For the first stick diagram, you had an output coming from B and D. I didn't get why it would be
This
wrong.
one?
Yeah, I didn't get why it would be wrong to connect it to C. You said it's getting shorted.
Yeah, let's look at this part, okay? Let's look at this part. 1, 2, 3, 4, 5. 1, 2, 3, 4, right? So first has to go through A first. That's A naught. Okay? And then we have to have two parallel transistors. We can definitely do it by doing this, because it's gonna have two parallel transistors and merge over here. But the problem is this one is in the middle. I cannot short it to the rest, the last one. There's no way to connect it to this one correctly.
Why not go?
Why not going this way?
Yeah.
Yeah, because if it goes this way, which means you are letting this current going through this channel, and eventually merged at VDD. So it's basically going through here and go to VDD. Right? Because after this terminal, they are sharing a terminal over here, so eventually it goes up to VDD. So it becomes impossible. That's a problem. So this is not working. So I have to swap it and move it to the top. Just one single transistor on the top. Any other questions on this? Is that clear? 50%? 90%? No? Let's look at the simple one. A, B, C naught. According to the conclusion, PMOSes on the top are in parallel and series. Parallel. NMOSes at the bottom are in series. So this becomes ABC naught. If you don't believe me, you can just list all these truth table and find out the outputs. It's gonna work. Okay? 8 entries from 000 to 111. Okay, can go through all of them and look at the PMOS and NMOSes if they are open or on or off, right? So you can find out the output. Eventually, it's the same as the truth table, the NAND gate, 3-input NAND gate. What about the stick diagram? So definitely 3 transistors on top, so 4 nodes. How do you do 3 parallel transistors? This is a pattern you want to remember, okay? You want to memorize. It's 3 input, 4 input. It's a certain type of connection. It's always like that, it's not changing. Boom, boom, like this. And that is 3 parallel transistors. How do you remember that? 2, 3, 4. 1, 2, 3. That's it. Okay? So 3 parallel transistors are always like that. So that's the VDD, current coming down from the VDD, and split, going here, split, split, because these are shorted, so they are equivalent. So it's basically 3 branches. It's 3 parallel branches. So
What would happen if I did it from the first to the last node? Would it say
then what? You short the 2 nodes, right? There's no voltage difference anyway for this one anymore.
so that just says A and C is in parallel?
Yes. So this one is not existing anymore because it's just 1 wire. So eventually, one VDD comes down here, and it's going to find a shortcut through the 2 wires and going down to the NMOSes. So this one is getting shorted. Nothing's going through this channel. It's just two transistors in parallel. So can you understand why this is 3 transistors in parallel for now? Yeah, sort of. They're equivalent. If you connect it this way, they're equivalent. What about 4? Like this. 1, 2, 3, 4, 5. 1, 2, 3, 4. Just keep in mind there's a certain way of doing that, okay? One, 2, 3, 4. Okay? Just memorize it. So the 3 parallel, 4 parallel, if you know how to do it, it'll be really helpful. So apparently you guys are not ready for the quiz. Let's do it on Friday.